is AE0 over D. Okay, so then that's going to be what? That area is going to be easy, right? Just 2 times 1, 8.854. I want to use the third digit too. It makes it a little bit more accurate. 8.854 times 10 to the minus 12 over the distance between them, so 0.0001 meters. Okay, so that's the initial capacitance. Where's my... Two times 8.854, 17.7, and then this is divided by 0.0001. Okay, so then it's going to be this number times 10 to the minus 12. So then you can go 1, 2, 3. So 177.08 nanofarads. 177.08 nanofarads. I could have said 177,080 picofarad, right? But then I go to the smaller, to the bigger unit, the nanofarad. Okay, so we answered that. So then how about the other questions? Q, U, E. So Q is going to be, so what's the voltage difference going to be between the plates? You know what? We could have asked here, even though it might have been redundant, we could have also said, calculate the charge, the energy. We could have said, calculate the voltage difference between the plates. So because then we can answer it for all the situations. So of course, that's the easiest one to answer. If it's connected to a 12-volt battery, the voltage difference is 12 volts. So then V is 12. So I'll circle the answers. Of course, then the next thing would be to calculate Q, how much charge will have built up. So remember, this is your working equation. It actually is the definition of capacitance, Q over V, right? So Q will be CV. So just take this C and multiply it by 12. Divided by 1,000. Okay, so we could say, well, I could go to a microcoulomb. So I could say 2.125 microcoulomb. Okay, so I'm going back 3 spaces and then changing it to a micro and then 2.125 microcoulomb. Okay, so now we know the charge. Okay, what's maybe the next thing is to do the electric field. Electric field between the plates would be what? Sigma over E0, right? Electrical field strength would be it's the sum of the electrical field created by 2 parallel plates. So you're adding them. That'd be Q over AE0. So we already know the Q is the 2.125 microcoulomb divided by A is 2. And then E0 is 8.854 times 10 to the minus 12. Oh, wow, the electric field was strong. You see, that's a really strong electrical field. Wow. So then you're going to have here 2.125 divided by 2. Divided by 8.854. And then you have that number times this one is going to go to the top. This is a 10 to the minus 6, and then that's 10 to the 12th, and then it's going to be mega 10 to the 6th. So it's going to be 0.12, and then just a bunch of zeros. So 0.12 mega newtons per coulomb, or you could say volts per meter. Okay. 0.12 mega volts per meter. Okay. So then the next thing is the potential energy, right? Potential energy stored in the chart. So we've got the C, we've got the V, we've got the Q, we've got the E, and the potential energy half Q squared over C. That's the base equation, the main one, right? But I don't necessarily have to use that. I think this is probably easier in this case because the voltage is just 12 volts. Here, I would have to deal with two things that are small numbers. I prefer this one. Half. The capacitance was what? 177.08 nanofarads. And then the voltage was 12 volts. Right? So then I don't have to deal with two things that are micro or nano. Okay, and that's it. So then that's going to be okay, so then it's going to be 12 squared divided by 2 times 177.08. Okay, then convert to micro. It's going to be 12.75 microjoules. Okay, so now we have the stored energy in the capacitor. Okay, the last thing was the energy density. Energy density is the energy per unit volume. Per unit volume of it's joules per cubic meter. So it's unit volume of for every per unit, every volume, how much energy is compacted in that area. So then it's going to be 12.75 microjoule over what would the volume of the capacitor be? The area times the distance between the plates, right? Area times distance. Okay. So just answering all that is quite a bit of work already. Okay, so then 12.75. Oh, so then it'll be area is 2, and then the distance is 0.0001. And then this is micro. So 12.75 divided by 0.0002. So the energy density is 63. So that's micro, 63,000 micro, or you could say 63.75 millijoules. Millijoules per cubic meter. 63.75 millijoules per cubic meter. Okay. Probably you don't have, do you have any questions on that? It's a lot of kind of, that one didn't require that much thinking. That one, it didn't require that much thinking. It's just more probably basic. But if you have any questions, yeah, ask. C, capacitance. C, voltage, we already know. The charge, the electric field. It's like one flow, it's like a domino effect. Once you know one of them, then you're just kind of flowing through, and then you're getting the energy and then the energy density. Okay, so now if a dielectric, so the battery is still connected, and then you place a dielectric. So then now answer the same questions. V, C, Q, U, E, right? So the fact that the battery is connected, that forces the voltage to be what? The voltage stays at 12 volts, right? So no matter what you do to this, whether you change its capacitance, you ask more charge from the battery, you know that the battery is going to do its utmost to keep the voltage at 12. This is actually going to help you in yesterday's lab, right? Because that's what you do in the lab. In the simulation, you put the battery connected, then you put the dielectric in, and then you disconnect the battery, and then you also put the dielectric in. So I think this is the same kind of things that the simulation asks you to do, right? So the first thing that we'll say, if the battery is connected for question C, is the voltage will be 12 volts. How about the capacitance? Is that going to stay the same? If you put a dielectric in there, what happens? Does capacitance stay the same? We have a equation for that, right? Capacitance with a dielectric is kappa times the capacitance in with air or vacuum. Vacuum, the air's dielectric constant is almost 1. So the capacitance for vacuum and air are about the same. So, so the capacitance goes up by a factor of the dielectric constant of the material you're putting. So what was my capacitance from before? 177.08. So basically this goes up to 1770.8 nanofarads. 177.08 nanofarads. Okay, so I think the rest starts kind of falling. Once you get this, the rest starts falling like a domino effect. What's going to be the charge? So you're increasing the, let's see here, Q is CV. You're keeping this the same. You're increasing that tenfold. So then the charge increases tenfold. Okay, so then the charge becomes 21.25 microcoulombs. Right? And then what does the, what was the next one? What does the electric field become? So the charge increases by tenfold, and the electrical field is sigma over 2 is 0. So yeah, if the charge increases, the electrical field increases by tenfold. So what would that be? 1.2 megavolts per meter. Oh, sorry. Yeah, it is 1.2. Yeah, it's 10 times this. So the electric field increases by that amount. Okay, so this is the one that I was talking about, where the app really has all these capabilities there. So you can put the battery at some voltage, let's say that, keep it connected, choose the area, whatever you want, have the dielectric out, choose the area. Okay, so now you can have electric field lines showing. You could have the capacitance showing, plate charge, stored energy, and then the voltage across the. So all these questions that I'm asking are actually simulatable, right? So this is the battery volt, this is the capacitor voltage right there, 1.5 volts. And then of course you could change the dielectric constant. So let's say it's 5. And you can choose specific dielectrics such as Teflon, paper, and glass. Cool, man. Wow. What else do you want? Okay, so now that's kind of what we did, is we kept the battery in place. We have the charge, right? And there's the electric field. So let's see what happens when I immerse this. So right now the capacitance is 0.29 picofarads. The plate charge is 0.43. The stored energy is 0.33. So then as I place them, what's happening to the charge and the capacitance? What was it before? 0.2. If you look at the capacitance, 0.29. Okay, then it went up so high, we zoom out, then it became 0.14. Well, actually it became 1.4 picofarads, right? So if we're right, based on our example we did, everything should go up by a factor of 10 except for the voltage, right? The voltage stays constant. So the capacitance goes up by a factor of 5, right? In this case, the plate charge also went up to 2.2 picocoulomb. And then the stored energy also went up. And then, of course, the charge went up. Oh, no, the charge, the charge already went up. They're showing that. What happened to the electrical field, though? What did we say should happen to electric field? This electric field here. Is that going up? Well, okay, my answer has a mistake. Yep. I caught it. And the simulation kind of got me to think, I'm making a mistake. Look at the simulation. Is the electrical field changing? No, I don't see more lines appearing. See, if the electrical field was changing, you would notice less field lines. You see here? This is what it means to electrical field to weaken until they go to 0. When the voltage is 0, there's no electric field lines, right? So when the voltage is negative, the electrical field is going the opposite way. It's going from the positive to the negative. You see? And then when you go oppositely, you see, for the field lines to increase, we would have to see more density of field lines, more of them. You see? Right, until I go there. Now, when I put the dielectric in there, okay, there's more charge building up, yeah. But is the electrical field increasing? No. The simulation is saying the electrical field is the same. So that must mean that this answer is wrong. You see that? So what's wrong with this? E is sigma over E0. My argument was, oh, well, if the sigma increases, right, if the Q increases, then the electrical field should increase by a factor of 10. No, it's not. Anyone have a clue what's going on? Well, actually, we haven't even had that lecture yet. It's going to come up later on. But maybe you might have a instinct. So basically, the electric field is staying the same. It's still 0.12. Wrong. Sad face. You have a clue? Anything, Daniel, on your part? What's going on here?
Well, I mean, initially I was thinking the same thing. I was like, wait, if the charge increases, right, then the charge density would also increase. But I mean, again, the simulation says otherwise.
Yeah.
I'm sure.
What do dielectrics do? They're polar molecules, right? Is anything ringing a bell? Do they create their own internal electrical field?
Oh, yeah.
Did you get the eureka? That was a small eureka moment.
Yeah, I see.
Yeah? I see. Remember the dielectric picture we saw yesterday? Especially this one. You see, the electrical field of the plates is from positive to negative. You see the blue line? But then when you place a dielectric in there, a dielectric is made up of a polar molecule, and the negative of the polar molecule faces the positive plate, and then the positive of the polar molecule faces the negative plate. And so the polar molecule creates its own internal electrical field opposing the electrical field of the plate. You see? So if kind of like this. So if this is the electrical field of the plate, and then you're putting that in, as you put the dielectric in, once it's fully inserted, the dielectric will have its own. So imagine this is negative, so this is positive, 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 negative, negative, negative. So then imagine this molecule looks kind of like this, positive and negative of the molecule, right? So the positive of the molecule will like to be next to the negative, and then the negative of the molecule wants to be next to the positive. So it creates its own electric field this way. The electrical field of the dielectric material is fighting against the electrical field of the plates. So the electrical field of the plate would like to be the value 12 millivolts. It would love to be that, right? Just by the equation sigma over E0. But the electrical field of the polar molecule will subtract from it a certain value such that the electrical field remains 0.12. It's not going to change. Right? And that's why the voltage difference between the plates is, what was it? 12 volts, right? That's why the voltage difference doesn't change. The voltage difference is equal to the electrical field times the distance between the plates. In other words, if we said the electrical field increased by 10 factor, by a factor of 10 to 1.2, oh, I wrote this wrong, sorry, 1.2. If it increased to 1.2, The problem with that is the distance is not changing. So if this changed to 1.2, this would have also increased by a factor of 10. You can't have the electrical field increasing and the voltage not increasing. You see? So something must be happening to fight the increase of the electrical field, and that's the electrical field of the polar molecule is fighting from it. So there'll be 1.2 minus some number is 0.12. So what is that number? 1.2 minus x is 0.12. X is 1.18. Let's see, 0.1281, right? All right, 0.12. No, 1.08. So that means the electrical field of the polar molecule is 1.08, right? So in other words, the electrical field of the plates would have wanted to be 1.2, but the dielectric is fighting against it by 1.08. If you subtract 1.02 minus 1.08, what you get? The original electrical field of the dielectric. That's why when I place this, this would have wanted to increase by 10 times. But as I place it, it's never increasing because this guy is creating an electrical field up in the up direction. That would have been a nice feature of the simulation if they showed a vector going up, you know. So then that vector would be 1.08 and it would fight against the electrical field of the plate. And then that could have been, yeah, what they could have done is show the black lines going down, increasing, right? Increasing, but then let's say blue lines of the dielectric up. We're asking too many things of these simulations, right? But that, you know, you could do that. These lines should be increasing going down, but then lines going up should be fighting against them, you see. Cool, huh? Okay, let's go this way. Have we answered everything? The energy went up by a factor of, so the electrical field stayed the same. Electrical field stayed the same. The energy went up by a factor of 10. That one is correct. The energy density, which is energy over volume, that should go up by a factor of 10. So 637.5. So the only one there that was kind of trickier was the electrical field, yeah. The other ones I think were more straightforward. Okay, how about if I place the dielectric halfway in? Let's see what's happening. And I go halfway. Something like that. Okay, so let's look at the original capacitance. So in this case, if I go, let's say this is 0.29, halfway in, it went up to 0.87. So what's that ratio? 0.29. That's about 0.87 divided by 0.29. So that went up by a factor of 3. So there we have to do some calculation why. So probably the charge went up by a factor of 3, the charge, but the charge distribution is not even, right? There's more charge on the right side, but this tells you the total charge of the plate, you see, the total charge here. But we could also ask, well, what's the charge on the right side of the plate or the left side of the plate? You see? So, but this one is the total charge. And then the energy also went up, right? But again, the voltage is staying the same. Okay, so let's solve that. So I think the trick here is to solve the capacitance first. So if you have question D, right? So if you have a dielectric, halfway in, kappa is 10, and then here is air, so just kappa is 1. Kappa is 1 is basically like your air or vacuum. So this would be two, they act as two capacitors in what? So if this is the battery, they act as two capacitors in parallel, right? So this is separate capacitor, this is separate capacitor, and they both have the same voltage. So voltage from here to here is 12 volts, and the voltage from here to here is also 12 volts. So this is 12. So this one would be C1 and C2. So what would C1 be? It's got the same K as before, but half the area, right? Half the area. So then it's basically half of the capacitance of the of the first one. What was that? Half the capacitance. So it was half of 177, right? 177.08 over 2. So let's see what that is. What is that? 8, 17, 8, 10, 5, 4, 88.54. That'd be what? Nanofarads. That's the capacitance of the left side of that. And then the capacitance of the right side would be 10 times this value, right? Because it has the same area as this guy, but it has a dielectric constant 10. So 885.4 nanofarads. So then how the capacitors add up in parallel, then the sum of their capacitance, you just add them like that. C1 plus C2. So 885.4 plus 88.54. 973.94. Okay, I think once we get the C total, that's basically getting this, right? What was my other C total? Yeah, it was 177 was the C total. So you see it went up. So it didn't go up by a factor of 10, of course. What factor did it go up by? See, when I placed the dielectric all the way in, then the capacitance goes up by a factor of 10 all the way to 1770. 1770. So what is this? By what factor did it go up? Divided by 177.08. 177.08. Oh, went up by a factor of 5.5. It probably has to do with the math of how this works. Yeah, because I'm putting in the 10 in there, but it's only occupying half the area, then together with another capacitor. Yeah, I see. So then, yeah, I can kind of see where that comes from, because it's 10, but it's only half the area. That's going to be 5. Then this one has a dielectric constant of 1, or then 0.5. I see. So the factor is a factor of 5.5. Do you see that? So yeah, you can kind of do that almost in your head. Although I wouldn't recommend it on the test, but you would say, okay, this is 10 and 1, so this would have increased the capacitance by 10 if fully inserted, but it's only half the area, so it increases by 5, and then this has half the capacitance of that, 0.5. Okay, so then everything else would go up by that factor too. So now it's a trickle down effect. If I want to calculate the total charge, what was the next thing to do? Oh, the voltage is going to be, the voltage is going to be 12 volts. The electrical field is going to be the same. That doesn't change, 0.12 megavolts per meter. The charge is going to go up by a factor of, what is it? 5.5, right? So then it's going to be, what was the charge of the first one? Okay, the charge of the first one was microcoulombs, and I'm just multiplying it by that 5.5 factor. So the charge goes up by that factor of 5.5. What else do we need to calculate? The electrical field stays the same. The charge, capacitance. How about the energy? Half CV squared. So voltage stays the same. Now the capacitance goes up by a factor of capacitance goes up by a factor of 5.5. Okay, so the energy is going to go up by a factor of 5.5. So then it's just going to be 12.75 microjoules times 5.5. $70.125 microjoules. Okay, and the energy density goes up by a 5.5. So 63.75 times 5.5. This was millijoules per cubic meter. Now, one other question I could have asked along with all of these is if a dielectric is placed, I could have said, how much work does it take to push that dielectric all the way in? So how much work does it take? Work required. Work required to put the dielectric in. So you have to, if it's positive work, that means you have to push the dielectric in there yourself. You won't go in unless you push it. Negative work means if you release it, it's just going to go rush it in. So you're going to have to hold it to prevent it from accelerating, right? So then we can answer that. So how would we approach that kind of question, the work? So let's go back to the case where it was fully inserted, right? So the work required would be, how would we find that? We would say the total potential energy at the end minus the total energy at the beginning. U final minus U initial. So again, the calculator problem, if I lift the calculator to a higher potential energy, then I have to do positive work, you see. So then, in this case, the potential energy final was what? 127.5, and then the initial potential energy was 12.75. So of course, that means you're going to have to push it in. That's 114.75 microjoules. Is that micro? Yeah. That's how much work is required, you see. So when you're putting this in, you're going to experience a force back at you trying to resist it. You see here, as you're going like this, where's the charge coming from? The battery, right? It's battery. You're forcing the battery to do more work. So then this system is not going to like it, because things like to be at a lower potential energy, not higher. So since you're requiring more charge, the battery is now going to send more charge. You're going to experience a back force. So then you're going to have to push from this right side like this to force it in, you see? So you're doing work. So the work is the integral of the force that you're exerting over this distance, F dot dx, you see? So we could develop an equation for the force that you would experience, the force that you would have to push here, right? We could develop an equation for that force that you have to push as a function of the offset distance, you see, the 11.5. As you're pushing, it's going to get harder, right? So then we can integrate that, and then that's the answer that we would get, 114.75. You see, so the way that I'm showing you is the easier way, just by taking the difference of the potential energies. Okay, how about for the work required for the halfway in? Well, it's probably less work, right? Because you're only going to the halfway distance. So then, the work required would be potential energy final minus potential energy initial. Potential final would be the 70.125 minus the potential initial, which would be the, you know what, let me have that right next to it. Potential initial was what? 12.75. .38 microjoules. So less work is required to put it halfway in. Okay, now let's go to the disconnect everything. Okay, so now go to the last part. Now disconnect battery. So see the plate already has charge. Disconnect it. Okay, now put in your dielectric and repeat the steps. Now what happens to the voltage? Now look at what happens to the E field. Look at what happens to the capacitance. Look at what happens to the plate charge. Okay, so let's go through that. Oh, what's happening to the voltage? So concentrate one at a time, you know, and keep doing that until you kind of get it. So let's first look at the voltage. Okay, so by the time it's fully inserted, the voltage went down by what factor? Well, it was at the beginning, it was 1.5 volts. And when it's fully inserted, it went down to 0.3. So that's a factor of what? 1.5 over, yeah, basically you're dividing it by a dielectric constant of 5, right? So the voltage now goes down by a factor of 5, if fully inserted, right? So it goes down by the dielectric constant of the material. So then what happens to the E field, of course? Look at the E field, you see? Look, remember the original E field? Okay, so the E field went down by a factor of 5, I'm sure, right? What happened to the capacitance? What happens to the capacitance? Actually, the capacitance goes up, right? Well, that's always the case. When you put a dielectric in it, it goes up. And by what factor does it go up? By a factor of 5. You see? So now concentrate on plate charge. So look at the red line. Wait. It looks like here the plate charge is changing, but here the red line is saying nothing. Here, let's see. I think the distribution of the charge is changing, how it's distributed, but the total charge has to stay the same. You see? So when you first put it in, it looks like it's changing a lot. You go like that, you go like that. But then by the time it's fully inserted, it looks like the beginning. You see, because the thing is, the idea is that the charge has nowhere to go. It can't go back anywhere. You didn't ground it to the ground. So it can kind of shift positions. See, if you're half inserted, yeah, there might be more charge here than here, but the total is still the same. The total charge is always staying the same. It's just there's more charge on the side where there's a dielectric, you see. Okay, but so therefore the total charge is not changing. How about stored energy? What's happening to the energy? So the energy is going down by a factor of 5. Okay, so you get the idea? So then what should happen? How do we solve all of these? Once you get the idea, you can just use the same factors that we have been using. What should happen in question E? So, voltage, charge, electric field. What other things do we ask? Potential energy. Final, the work required to bring in the dielectric. What else were we asking? Potential energy density. Right? So what should be the voltage if I fully insert it? So in my case, the dielectric constant is 10, right? So the voltage should go down by a factor of 10. So it should be 1.2 volts. What should be the charge? Stays the same, right? So 2.125 microcoulombs. So I'm looking over at the answers from the first case. So this is fully inserted. Okay, and then E, the electric field, what should happen in that case? In the previous case, the electrical field stayed the same. Here, actually, it should go down by a factor of 10, right? Because the charge is going down. And no, sorry. The charge is staying the same. But as you're inserting The charge is staying the same, so the electrical field created by the plate is the same. But then as you're inserting a dielectric, the dielectric is fighting against you with 1.08. And the electrical field down, so the two are fighting against each other. You see that? The 1 point, what was it? The 0.12, the electric field of the plate is 0.12, and then the electrical field of the dielectric is fighting against it. So then what should be the final answer? The electrical field goes down by a factor of 10. So that would be 0.012, right? Megavolts per meter. Okay, potential energy final. What should that be? I don't want to use this version of the equation now. I want to use one of the other ones, half Q, yeah, half QV. In other words, I want to use one of the ones where I know one of them is not changing. You see here, C and V are changing, the voltage is changing, and the capacitance is changing. Oh, I could have answered the capacitance too, I forgot. The capacitance is going down by a factor of 10. So it's 17.70. No, actually, no. Why is it going down? It should be, yeah, it should be going up. See, I got confused even. So it should be, capacitance should be going up by a factor of 10. 1770.8 nanofarads. So capacitance goes up. It doesn't matter how you put the dielectric in. The voltage goes down. The charge goes down. No, charge stays same. Voltage goes down. Electric field goes down. Potential energy. So I'm going to use this version because I know that the charge stays the same. So the voltage goes down by 10. So then the energy goes down by 10. So this stays the same. And this goes down by a factor of 10. What was the initial energy? 12. So yeah, the initial energy was 12.75. So it goes down by a factor of 10. 1.275. Let me jump to the potential energy density. Then that goes down by a factor of 10. Okay. 6.375. And so then how about work? Well, in this case, if you let the dielectric go, the dielectric will actually rush into the capacitor because it likes to go from a higher potential. Its initial potential energy was 12.75, right? So it would like to rush towards that. So you're going to have to do now negative work, 12.75. You're going to have to do subtract these two. So the work you're going to have to do is potential energy final minus potential energy initial. So 1.275. 1.275 minus 12.75. You're going to have to do negative 11.475 microjoules. So the dielectric essentially would feel a force. As you bring the dielectric like this, the dielectric would feel a force that would push it in, right? If the battery is disconnected. So you're going to have to exert a force like this, work external. So you're going to have to hold it and put it in at constant speed. So that's what it means to do negative work. Okay, well, what if it was halfway in? I'm not necessarily going to answer it because everything is the same except the factor that it changes by is 5.5. You see? So then the voltage will go down by a factor of 5.5. Capacitance will go up by a factor of 5.5 if it was inserted halfway in. Charge will stay the same. This will go down by a factor of 5.5. This one will go down by a factor of, see, now everything is going down by a factor of 10. And then this is also going down by a factor of 10. And then the work, you're just going to have to calculate a new work for the halfway in. Okay. Good. So that problem was easy and yet kind of hard, had lots of parts to it, but it teaches you a lot of those basic things. So when we come back from the break, we'll do several more capacitor type problems.